Gyroscope technology and applications, reviewing the industrial perspective. The term gyroscope, conventionally referred to the mechanical class of gyroscopes, derives from the ancient Greek language, being the physics of the precession motion, a phenomenon also observed in ancient Greek society. Gyroscopes are devices mounted on a frame and able to sense an angular velocity if the frame is rotating. Many classes of gyroscopes exist, depending on the operating physical principle and their involved technology. Gyroscopes can be used alone or included in more complex systems, such as gyrocompass, inertial measurement unit, inertial navigational system, and attitude heading reference system. In this paper, a review of the more commercially diffused classes of gyroscopes is presented. For all classes of gyroscopes, being angular velocity sensors, the major issues are related to the errors in measuring the angular velocity. For this reason, one of the more important merit figures is the stability of the scale factor. Scale factor represents the sensitivity of the optical gyroscope, while the accuracy of the gyroscopes, which is inversely proportional to the sensitivity and takes into account the measurement errors due to the noise, can be expressed through the resolution R, or in the RLGs by the angle random walk ARW, linking R with the bandwidth B of the measurement system through the equation ARW equal to R divided by 60 square roots of B. Minimum scale factor stability leads to small sensor errors and requires better instruments and improved accuracy, bringing higher costs of the system. Thus, gyroscope performance and costs are directly related to the application requirements. Since the 19th century, mechanical gyroscopes, classified as displacement gyroscopes and ray gyroscopes, are the historical ones, consisting in a toroid-shaped rotor that rotates around its axis, while since the 20th century, optical gyroscopes operate by sensing the difference in propagation time between counter-propagating laser beams, traveling in opposite directions in closed or open optical path. The main diffused types of optical gyroscopes are IFOG and RLG, which both exploit the physics of the Sagnac effect. For applications requiring very high performance, the ring laser gyroscope is currently more diffused and has the bigger market share. Mixture electromechanical systems, which are called MEMS, gyroscopes, are motion sensors that detect and measure the angular motion of an object. They measure the rate of rotation of an object around a particular axis, 1 axis, 2 axis, and 3 axis. Although initially used for expensive military applications, now they are also adapted for low-cost commercial applications of consumer electronics for automotive, defense, industrial, and medical applications. The increased demand for mobile services is also responsible for the growth of the MEMS gyroscopes market. The cost of MEMS gyroscopes is expected to reduce drastically in the next years, leading to an increment in the use of these devices. The MEMS and optical gyroscopes, in particular interferomic fiber optic gyroscopes (IFOG), are replacing many of the current systems using ring laser gyros (RLGs) and mechanical gyroscopes. However, among the optical gyroscopes, applications requiring extremely high scale factor stability continue to be achieved only with RLGs. The scale factor stability, expressed in parts per million as function of the bias stability, is reported in Figure 1. Depending on the scale stability, an extensive range of applications is considered with reference to the gyroscope technology, and performance in terms of scale factor stability versus bias stability is also in this text. Better performance, such as the highest cost and the smallest production volume, are related to the gyroscope technologies placed at the left bottom corner, while the lowest performance, such as the lowest cost and the higher production volume, are placed at the right top corner of Figure 1, including the consumer electronics applications. Among the gyroscope technology in these reviews, we cover the more diffused and commercial gyroscope technologies: mechanical, RLG, IFOG, and MEMS, with the relative applications reported in the following figure. Mechanical gyroscopes. A mechanical gyroscope essentially consists of the spinning mass that rotates around its axis. In particular, when the mass is rotating on its axis, it tends to remain parallel to itself and to oppose any attempt to change its orientation. This mechanism was invented in 1852 by physicist Léon Foucault during his studies of the Earth's rotation. If a gyroscope is installed on gimbals that allow the mass to navigate freely in the three directions of space, its spinning axis will remain oriented in the same direction, even if it's changed direction. A mechanical gyroscope shows a number of physical phenomena, including precession and nutation. In the following sections, the main operating principles of the mechanical gyroscopes are reported, with reference to the inertial navigation systems. Gyroscopic effects. The basic effect upon which a gyroscope relies is that an isolated spinning mass tends to keep its angular position with respect to an inertial reference frame, and when a constant external torque, respectively a constant angular speed, is applied to the mass, its rotation axis undergoes a precession motion at a constant angular speed, respectively with a constant output torque, in a direction which is normal to the direction of applied torque, respectively to the constant angular speed. External forces acting on the center of mass of the rotation part do not affect the angular position of rotating axis. Mechanical displacement gyroscopes. The primary application of gyroscopic effects consists in the measurement of the angular position of a moving vehicle. The spinning mass is mounted upon a gimbaled frame, allowing rotation along two perpendicular axes. The gimbaled frame of the gyroscope is attached to the vehicle and it is free to rotate, while the rotation axis of the spinning mass keeps its angular position during the motion of the vehicle. The variation of the absolute angle of the vehicle can be simply associated to the respective variation of the angle between the rotation axis of the mass and the fixed direction on the frame of the gyroscope. Another useful application of the physical effect is that exploited in gyrocompasses. When external torques are not applied to the frame, the gyrocompass keeps the angular position of a pointer to north direction, independently of the path followed by the vehicle. The advantage of such a mechanical system is that it is immune to magnetic fields that can cause deviations on the pointer angle. Mechanical ray gyroscopes. Ray gyros measure the angular speeds of a vehicle during rotary motion. According to equation, it is possible to notice that when an angular speed is imposed to a gimbal and hence to the spinning mass, a proportional torque appears along a direction that is perpendicular to the direction of an imposed angular speed. If a spring system of known stiffness is opposing and balancing the output torque, it is possible to compute the imposed angular speed through the measurement of the output angle, assumed by the inner gimbal frame over time. Description of common mechanical gyroscopes. A mechanical gyroscope consists of, firstly, a spinning wheel mounted on two gimbals. This allows it to undergo precession motions along two perpendicular directions. Secondly, a rigid frame with rotating bearings. The mechanical components in relative motion are subjected to friction, which in turn leads to measurement drifts over time. The main goal in gyroscope design is to build a frictionless and perfectly balanced device. To minimize friction, high-precision bearings and special lubricants are used, or in many critical applications, magnetic suspensions or fluid-suspended configurations. Thirdly, sensing systems, pick-offs. These are capable of reading angular displacements between the two adjacent gimbals and to transduce them into electric signals by means of potentiometers, resolvers or encoders, thus constituting the input for a computing unit.